Welcome to my presentation on interconnection and smart control of district heating networks for increased flexibility. My name is Jakob Binder, researcher at AEE Intec, and as you can see, the content of the presentation is based on results of AEE Intec and our partners Best, Schneid and Backend Partner. The research on the presentation topic was done within the Austrian flagship project ThermaFLEX. It combines concept development with a strong focus on demonstration, considering technical components, system approaches, and also non-technical measures to increase flexibility within the district heating sector. In total, 11 demonstration case studies are carried out with different district heating operators in Austria. Some of the covered topics are heat pump applications, waste heat utilization, large solar thermal plants, smart control approaches, network interconnections, and also combinations of multiple of these measures. This presentation focuses on the demonstration 100% renewable district heating Leibnitz in the south of Austria. The schematic map gives an overview of the district heating network and the measures in Leibnitz. Besides the modernization and optimization of the existing heating plants, the core measures are a smart control strategy for the overall system, as well as the interconnection and massive expansion of the two district heating networks, which you can see in blue and green. In addition, we have the waste heat utilization of a rendering plant, the management of several storages, and the low temperature network fed by the return of the main network. The technical measures were complemented with a stakeholder and user integration process. One of the main stakeholders was the city of Leibnitz. The main idea behind interconnecting the two networks was the availability of waste heat in the southern network. In winter, the demand, which cannot be covered by waste heat of the rendering plant, is covered by a gas boiler, and in summer, surplus heat is available for the northern network. The situation within the northern network, supplied only by biomass boilers, is the exact opposite. In winter, the boilers are operated below nominal load, while in summer the operator faces an inefficient partial load operation. Thus, the interconnection of the networks results in a win-win situation. In general, interconnections of district heating networks, but also interconnections of branches or subnetworks within large district heating networks, are able to offer the following benefits. It can save costs of peak load or backup boilers. It can free up production capacity for future network expansions or additional consumers, and it can increase flexibility and security of supply of the network due to the enlargement of the pool of production units. Usually, the biggest challenge is the change of heat transfer direction, which comes with water hammers, especially at high volume flows. Also, temperature cooldowns have to be avoided. If the direction changes too often in a short period of time, it can happen that the water is pumped forward and backwards without passing through a heating plant. But both challenges can be coped with a well-adjusted control system. On the right, you can see the hydraulic scheme of the installed bidirectional heat transfer station. It is able to transfer a nominal load of 4 megawatts. To coordinate all production units of the overall system, Best introduced an energy management system, which is considered the master control system. Based on a weather forecast, measurements, and the experience of the model predictive control system, the optimal operating strategy for the next 24 hours is defined every 15 minutes. Based on the optimal strategy, set point values are sent to the lower control level. For example, the required load of the boilers, the state of charge of the heat storages, or the load and direction of the heat transfer station. These diagrams show the operation of the three heating plants Tilmich, Keindorf and Gabersdorf, including its storages and the heat transfer station. Left to the dashed line, you can see the measurement history. Right to the dashed line, the plant operation is shown. Due to restrictions of the lower level control system and intervention of the operators, during the test phase, the recommended control strategy wasn't always accepted so far. But in the lower left diagram, it is shown clearly that during this time period in April, the operation of the backup gas boiler at the rendering plant could have been avoided with the EMS. The first estimated results compare the overall system with separated and interconnected networks. Both cases use the EMS as an overall control system. Applying the interconnection enables a reduction of 9% in operating costs and a reduction of even 45% in CO2 emissions. The main reason for that is the reduced operation of the gas boiler. At the same time, the costs and emissions of network 2 increase, which has to be compensated by the heat price network 1 pays to network 2. Independent to the EMS, demand-side management routines are applied to the consumer substations, which are equipped with Schneid's control system. The DSM is active for about 50% of consumers within the aggregated network. That corresponds with 30 to 50% of the total load. The DSM shapes load peaks by setting load limits and fills load values by forcing consumption of selected substations. Undersupply of single substations is prevented at any time by setting a minimal temperature limit for the delivered heat. The picture in the left shows a consumer with intermittent demand, orange line, the nominal load, green line, and the actual load limit, blue line. The picture in the right shows the same values for a consumer with continuous demand. Both pictures show a load limit of roughly 50% of the nominal load during 6 and 12 am, leading to a kind of forced load peak by increasing the limit right afterwards. First estimations showed that the DSM is able to achieve a peak load reduction of the overall demand of about 5 to 10%. These values are based on the mentioned DSM coverage of 50% of all consumers. Summing up, first results of the test operation phase of the interconnected district heating networks combined with an energy management system and demand-side management showed a reduction of peak loads, a reduction of operating costs, and also a reduction of CO2 emissions. The main challenges were and are the interfaces between the standard control system and the energy management system, as well as the different interests of operators which have been changing with the ongoing expansion of the networks and the increasing heat demand. If we can keep the schedule, the test operation phase should end in February 2022. Finally, the potential for interconnections of district heating networks in Austria shall be estimated and best practice reports as well as rollout strategies shall be developed. In the end, to those who are interested, I would like to point out that AEE Intec is going to host the second ISEC in April 2022 in Graz. The call for abstracts is open until the end of September. Finally, I hope I could give some valuable insights into the ThermaFLEX project and the demonstration case of Leibnitz. For further information, you're welcome to contact me, or you can also visit the project homepage. Thank you for your attention.